Okay, I think it's a good time to start now. People are coming in, but at some point we simply have to take off. So I'm extremely happy to host this second edition of qmeets, this time with a topic which is more related to ultracold matter and also topological matter. And we are extremely happy and grateful that we got two excellent speakers for this second episode. That is first Nathan Goldman, who is actually not far away from me right now because we are both in Brussels
Mhm.
at another campus, and I'm actually at home. So, for those of you who don't know Nathan, he is probably one of the most important people currently working on topological quantum matter. He has studied most of the time at the same university I'm currently at, ULB in Brussels, and at some point after some time in Paris, in Jean Dalibar's group, he returned to ULB, forming his own group there. He's currently holding an ERC grant, so has a lot of money to do a lot more exciting research. And I'm very happy that you agreed to give this first theoretical introduction to fractional quantum Hall physics. On the other side, we have Julian Leonard, who did his PhD, if I remember correctly, in Vienna, and then moved to the group of Markus Greiner. Probably all ultra-cold atom people remember this name, to do the research we will be hearing about today. And then 3 years ago, he got his own group in Vienna, is now building up not one, but three experiments to do many, many things. And I'm very sure that in the future we will see a lot of nice results also from the Leonard group. So without further ado, let's start right into the action. And the stage is yours, Nathan.
Thank you very much. Well, first of all, thanks a lot for this very kind invitation. I think it's very exciting to have these kind of talks. And today, the focus will be set on realizing and characterizing fractional quantum Hall physics using ultracold atoms in optical lattices. So as you understood, I will start with the theoretical concepts, which are really at the core of this physics, motivated from the point of view of cold atoms. And then we will have Julian really doing the hard work, explaining what is actually done in the experiments. So let me start with the physical setting. So in this talk, we will be really focused on the systems of ultra-cold atoms in optical lattices. So what you should have in mind from now on are neutral atoms, which can either be bosons or fermions, hopping on a lattice, as represented here. The lattice is created externally by light, and these atoms can interact. They will typically interact on site through either attractive or repulsive interactions. Now, as I said, the lattice can be created externally. Now, the lattice can be one-dimensional, two-dimensional, three-dimensional, and it can have different shapes, right? We can have different geometries. One can design square lattices, honeycomb lattices, triangular lattices, kagome lattices, and so on and so forth. So in this talk, we will be focused on the case of 2D lattices, but you should keep in mind that this can be generalized. So the general setting that you should have in mind now are essentially neutral atoms that you would load into such a band structure. And we have this freedom of really tuning this band structure in the presence of interactions, potentially very strong interactions among the atoms. So very generally, as you probably understand from this short introduction, this is a very rich playground for many quantum physics. In this talk, we will mainly be interested in ground state physics, right? So we will be thinking about the properties of the ground state and low energy excitations above this ground state. But one could also do time-dependent things, look at dynamics, which could be very relevant in various contexts. For example, in the quantum simulation of lattice gauge theories, for instance, but which will not be the topic of today's talk. Now, as I said, today's talk will be focused on realizing and characterizing quantum Hall states in these settings of cold atoms and optical lattices. So in the next couple of minutes, I will ask you to just forget about cold atoms and optical lattices. I will just try to motivate um, these quantum Hall states, why we find these interesting. They were discovered in the solid state, but they have very universal features that we are interested in and which could be nicely studied with cold atoms, as I will try to argue. So as I said, forget about cold atoms for a second. Think about charged particles, let's say electrons, in a 2D plane in a strong magnetic field. And we are interested in the ground state of such a setting in the regime of strong interactions. Okay, so what I have in mind now are correlated states of matter in a very strong magnetic field. Now, to give you a hint of the kind of structures that would appear in such a ground state, let me just highlight a few very basic features. So let's just start with a free particle, just one free particle in free space. So the dispersion for this particle is just this parabola. Now let's take two particles. So we would now have two interacting particles, and let's take the interactions to be repulsive. Now, if I take two particles and I bring them close, I will accumulate a lot of interaction energy, potential energy, and this can actually be converted into kinetic energy, okay, as represented here. So that means that if I solve this two-body problem in the continuum, in general, I will have continuum energies of scattering states. Now, the situation is very different if you consider particles in a magnetic field. Consider now a single particle in a magnetic field. If you solve the energy spectrum, you will not find a parabola. You will find what are known as Landau levels. So these are bands which are completely flat. Okay, these Landau levels are separated in energy by an amount h bar omega c, where omega c is the cyclotron frequency. Now, this has a very important impact on the physics of interacting particles. And just following the same logic as above, let's now consider two interacting particles in a single Landau level. In this case, you immediately see that the story is very different because the kinetic energy is quenched, right? When you take two particles, you bring them close. It's no longer possible to convert all the potential energy into kinetic energy, which means that in this setting, if you restrict yourself, to a single Landau level, the eigenstates of your two-body problem are now bound states, right? The particles cannot fly away, they remain bound. And most importantly, the spectrum of this two-body problem is now discrete, right? There are gaps between these different states, and these gaps will play a very important role in the following. Now, as you can see in this little sketch, these bound states are not arbitrary, right? What one can show is that because of the presence of this magnetic field, these particles will actually undergo orbits around each other, right? And so you can see that the relative motion of this two-body problem is associated with a certain angular momentum. And this motion comes with a certain orientation, with a certain chirality, which is imposed by the external magnetic field. So what I've been describing here at this level is the physics of two particles in a magnetic field or in a Landau level. Now we're interested in what happens when you consider a many-body system in this magnetic field. And what you can show is that in certain occasions, and this will be the case for the so-called Laughlin states, the many-body state is very reminiscent of what I just described to you in the two-body problem. What you can find is that if you project the system onto the lowest Landau level, your particles will adjust themselves such that all pairs of particles undergo these pairwise vortex motion, or these little orbits that I was explaining a second ago. In fact, one can show that indeed by imposing these pairwise vortex motion among all the different pairs in the system, this allows you to minimize the interaction energy. And if you think about projecting the system onto a single Landau level, of course, interaction energy is all that matters because the kinetic energy is quenched. And so what I'm describing here is actually the Laughlin wave function, which, as I said, describes a certain class of quantum Hall states, the so-called Laughlin states. And what you can immediately see from this picture is that because of this pairwise vortex motion of every pair of particle, there are extremely strong anti-correlations at short distances. And this is something that Julian will comment on in his part as well. Now, this Laughlin wave function is one of these many body wave functions that were proposed to capture the physics of quantum Hall states. There are many other wave functions, but what I would like to do now is just list, and I will not have the time to go through all these features, but to list some general striking features of fractional quantum Hall states in general. Now, the first very important point is that the many-body ground state, so these fractional quantum Hall states that I've just been describing, are incompressible. Okay, so the ground state is gapped. And the state is gapped not because it's a band insulator. These states are gapped because of interactions. And somehow this gap, which exists above the ground state, is reminiscent of this discrete spectrum that we already find at the two-level bound state level. Now, another property which is extremely important is known as topological order. Its definition, its most fundamental definition, is very abstract. The problem is the following. Try to get the ground state of this many-body problem on the torus geometry. And what you will find is that if you have a fractional quantum Hall state, this ground state will automatically come with a degeneracy. And this degeneracy cannot be removed by small perturbations. Okay, so there is a very robust ground state degeneracy, and it has a topological origin. That is, it's something you cannot remove easily. Now, something that directly derives from this topological order is that the elementary excitations, particularly the low energy excitations above this ground state, are fractionally charged. So you start with a system, say, of electrons in a magnetic field. Your electrons have, unit charge. Well, the elementary excitations on top of your ground state have a fractional charge, 1/3, 1/5, etc. And these fractionally charged excitations, they also obey a different statistics. They are no longer bosons or fermions that actually satisfy fractional statistics. So these excitations are known as anyons. So they represent one example of anyons in nature. Now you can do transport experiments, right? You have your ground state, and now you might want to excite it a little bit. You might want to do some linear response. And if you look at transport, you will see that the whole response, so if you look at the whole conductivity in this system, is quantized. This is why these states are actually known as fractional quantum Hall states. The whole response is quantized, and it is actually fractionally quantized. Now, another interesting fact is that there is something very special that happens on the edge of these fractional quantum Hall systems, which are that you have gapless excitations, which are chiral. They're typically chiral. So the idea is that you have this system which is gapped in the interior, in the bulk. This is what I told you. The ground state is incompressible, but it is really incompressible at the interior of your quantum Hall droplet. But on the edge of your droplet, you have these gapless chiral edge excitations. So such that these quantum Hall states are actually instances of topological insulators, right? These are insulators because they are incompressible in the bulk, but there is something topological which imposes something non-trivial on the edge, and these edge excitations are exactly these special features. Now, the many-body wave function, such as the many-body wave function associated with the Laughlin state, so this Laughlin wave function, is topological in nature. That is, if you give me this many-body wave function, I can write down the topological invariant starting from this wave function. Okay, so that means that there is really a quantity, a topological invariant, a number that you can calculate from the many-body wave function, and that will remain essentially constant under smooth deformations of your system. And this many-body topological invariant is known as the many-body Chern number. Okay, so this is something that you can compute numerically, but it turns out that this many-body Chern number is also the quantity that gives its value to the whole response. And I will come back to this in a couple of minutes. Now, the whole response is something that you can measure in an experiment. You can also probe the chiral edge excitations. Now, there are also things that you might want to do numerically or theoretically, which is to look at fingerprints of these topological states in the entanglement spectrum. And I will come back to this in a couple of minutes, but I'm already emphasizing the fact that there are very important signatures, in fact, topological signatures, both considering geometric partitions, that is, cutting the system into two, for instance, but also particle partitions. And these two different partitions will probe different aspects of these topological states. Okay, so in the previous slide, I discussed the physics of charged particles, let's say electrons, in the 2D plane in a magnetic field. But what is very relevant for today's talk is to ask ourselves if quantum Hall states can actually be realized in a lattice environment. Are there quantum Hall states on lattices? So this is not only relevant for us in the cold atom community, it's also very relevant to the solid state community, where they achieved quite recently so-called fractional anomalous quantum Hall states in these moire systems. And the same question arises there. What is the right lattice configuration, or what are the properties of the bands, the Bloch bands that are associated with your lattice that will ultimately lead to fractional quantum Hall states? Now, you will ask me, what are the rough ingredients, right, that you would need to have a good band structure, right, to have good fractional quantum Hall states? And the answer to that question is, on the one hand, very subtle, and it's actually a question which is still under exploration these days. But I will give you very rough ingredients at the level of this talk. First of all, we need to break time reversal symmetry, right? Quantum Hall states are associated with this notion of chirality, right? We have in mind that we will have these chiral edge excitations, so we somehow have to break time reversal symmetry. This could be done explicitly by imposing a magnetic field, as I just explained to you a couple of minutes ago, but time reversal symmetry could also be broken spontaneously, and this could also lead to fractional quantum Hall states. So this is not well, a statement about the band structure itself. It's more a general statement about the Hamiltonian in general. Now, what about the bands? So what I'm showing you here is just, some band structure. So this is a single particle energy spectrum for some particle in a lattice. And so suppose that I put some particles in one of these bands. So I would ask myself, what are the properties that this band should satisfy such that, putting some particles with the right filling in this band will lead me will produce a fractional quantum Hall state? And the answer to that is, well, we want these Bloch bands to be, and now using quotation marks, similar to Landau levels. That is, these completely flat bands that you get in the continuum limit, right? So flatness is kind of important. It's also quite natural to think that if you want a strongly correlated state, you basically want interaction scales, interaction energy scales to be large compared to a bandwidth. So flatness seems to be a reasonable condition to ask for. Now there is something which is more subtle, which is quantum geometry. So these bands are eigenenergies, but they are of course associated with eigenstates. And these eigenstates are associated with the quantum geometry. So you might have heard about the Berry curvature, the quantum metric. If you have the idea is that if you want a band to be relatively similar to a Landau level, you might want these quantum metrics and Berry curvatures to be as uniform as possible over the Brillouin zone. Now there are more abstract, more refined criteria. People talk about vortexability of bands, this idea that if you generate a vortex in your system, you will remain in the same band, right? You will not generate interband couplings by adding new vortices into the system. This is vortexability, and this is of course a condition satisfied by the Landau levels, but Bloch bands that satisfy vortexability seem to be pretty good bands for fractional quantum Hall states. And the last thing that I wanted to mention is, of course, interactions. To have fractional quantum Hall states on the lattice or in the continuum, you need, of course, interactions. And if you want to target a state like a Laughlin state, well, aiming for contact interaction is typically a good idea because the parent Hamiltonian to a Laughlin state would be a two-body contact interaction Hamiltonian, at least if, for example, if you have bosons. So a general term that people use to denote fractional quantum Hall states which emerge in lattice system. So this name is fractional Chern insulators. So we typically use both words, either quantum Hall states on the lattice, or fractional Chern insulators. And here's a relatively recent review that discusses this physics in general. Now, I just wanted to highlight one example which is particularly relevant for today's talk, which is related to a very early proposal by Sørensen, Demmler, and Lücken from 2005, which I believe is probably one of the very first numerical analysis of a fractional quantum Hall state on a lattice. So what is this model? Well, it's essentially the Harper-Hofstadter model. So if you forget about the many-body physics and put aside interactions effects, just take the Harper-Hofstadter model. So this is a square lattice with a uniform magnetic flux in each plaquette. And now the idea is to add hardcore bosons or strongly interacting bosons on this lattice. Okay, so you might want to call this model the Bose-Hubbard-Hofstadter model if you want. I might use this word later as well. So what Sorensen, Demler, and Lücken investigated numerically is a situation where the lowest band, so this is these bands that I'm showing here are actually bands of this Hofstadter model. So this is not a coincidence. And the idea was to put hardcore bosons in the lowest band. You see that this lowest band is relatively flat. And so they would put hardcore bosons into this lowest band with a filling factor, which is 1/2. Okay, so that's very important. This lowest band is partially filled, filling 1/2. In general, the filling factor is defined as the total number of particles n divided by n phi, which is the total number of flux quanta in the system. But you can just think of having this band being half filled, okay? And we know from the, well, the form of the Laughlin wave function that strongly interacting bosons at filling factor 1/2 in a band that is very similar to a Landau level, this should actually lead to a Laughlin state. So a state, a many-body state characterized by this Laughlin wave function, which I described to you a couple of minutes ago. So they did numerics on this, and here is one of the results. I'm showing you here the many-body gap here on the y-axis as a function of the flux. So you will see in the following, I use either phi or alpha, which is phi divided by 2 pi for the flux. But this is really just the flux per plaquette. And what they see is that this many-body gap is, well, non-zero. It actually increases with alpha, and then it reaches a maximum, and then it goes down. It reaches a maximum around 0.2. You might want to keep this value in mind because we will see this 0.2 in the following of the talk. Now, what is happening here, close to the small values of alpha, is actually very, very similar to what happens in Landau levels. Actually, what you can show is that when the flux alpha is very small, you actually recover the continuum limit. Okay, this is simply related to the fact that when the flux is very small, the magnetic length is very large, and so you basically do not resolve the lattice. Okay, so in this limit, you actually don't have lattice physics. But as you approach the value 0.2, the magnetic length is now very small, of the order of the lattice spacing. Remember, we are on a square lattice here. And now lattice effects become important. And these effects are typically detrimental. This is what you see here, right? So the many-body gap, which is, I remind you, what protects this ground state of interest, this Laughlin state, this gap goes down as you increase the flux. Now they calculated another quantity. This was actually calculated in a later paper in 2007 by Mamad Hafezi. They actually took that state that they had calculated numerically, and they calculated the many-body Chern number using that state numerically, and they confirmed that this many-body Chern number is indeed fractional. It is non-zero, but it is in fact fractional. It takes the value 1/2, which is compatible with a Laughlin state at filling factor 1/2. You might want, again, to keep this 1/2 in mind because this 1/2 will appear on several occasions. Okay, so the question is, can one realize this Hofstadter model with cold atoms? I will try to go quite rapidly on this. We have cold atoms, right? We don't have electrons. So we have neutral atoms. So the idea is it possible to design a system where you have neutral particles hopping on a lattice such that they actually feel the presence of this uniform magnetic flux? And if you look at things formally, you will see that this flux appears in the Hamiltonian through these complex tunneling matrix elements. And so there are various ways one can actually engineer these complex phase factors here. One way is to do Floquet engineering. So one idea is basically to create these Wannier-Stark ladders, then start modulating very fast the on-site energies. And what you can show is that the hopping matrix elements get renormalized and you get a complex phase factors. This is related to the phase of your modulation, so you can tune these things in the experiment. And this is something that Julian will explain in his talk. There are other methods, for example, laser-assisted tunneling methods, synthetic dimensions, and so on and so forth. Now, this model was realized experimentally, and Julian will, of course, explain this in detail. It was realized around 2013 in several groups in Munich, also at MIT. But just to emphasize the fact that about 10 years ago, the idea was to load weakly interacting bosons into one of these bands and to characterize the state that they would realize with these weakly interacting bosons. And so in one of these early experiments, the experiments of Monika Eidelsberger in 2015, what they did was actually to load these bosons in this band and then add a force and measure the Hall drift, right? The transverse displacement of the cloud in situ. And from this, they could actually extract the Hall drift or the Hall response and measure the Chern number of these Bloch bands. So this was actually the first time that the Chern number was measured in a cold atom experiment. Now, let me, yes, I still have a couple of minutes. Let me emphasize a very important point regarding the realization of topological states, or the preparation of topological states in cold atoms. So you might know that if the aim is to produce a topological ground state, it is essentially impossible to connect it adiabatically to a trivial ground state. So in an experiment, you would typically start from something trivial, something that you like, and you might want to try to connect it to a topological state. But this is by definition impossible because there is an obstruction because of this topology or this topological order. However, if you consider few atoms in a box, then what you can show is that, well, this crossing that would happen as you go from a trivial to a non-trivial state can be avoided, right? So here I'm introducing this little gap delta, which is a finite size gap. It really exists because of the smallness of the system. And this is an idea that was introduced about 20 years ago by Ignacio Cirac, Belén Paredes, and collaborators, and also considered by many people recently as a way to realize topological states starting from a trivial state in settings with only a few atoms in a box. So Julian will comment on this in a second. You can apply this directly to this Hofstadter model. Here you would have natural parameters which are given by Jx and Jy, which are the hopping matrix elements on your lattice. You also have the flux, which is another parameter that you can tune. And if you look at the energy gap, so here the color code corresponds to the energy gap of this system with a small number of particles, you will see that in this plane, which is given by these two parameters, so the tunneling ratio and the flux, there is actually a path, right, that adiabatically connects our fractional quantum Hall state, so a state that has the features of fractional quantum Hall physics, to a normal state, so a normal superfluid state that do not share those features. So it's exactly these kind of paths that will be exploited in the experiment. Now, one can envisage other ways. For example, one can use open system approaches. So this is something that we introduced quite recently, which is this cold atom elevator idea, where the idea would be to start with an empty system, but with reservoirs which are filled with atoms. Then you would lift up those reservoirs, as if they were little elevators, and particles would then be allowed to enter the system. And if you do this thing properly, you can end up with a fractional quantum Hall state in your system. So this is something that was investigated numerically by Botao Wang and reported in this paper that appeared last year. Now, let me just finish with a few words regarding the characterization of these strongly correlated topological states. So imagine that you indeed have a few atoms, let's say a few bosons, in a box, in an optical lattice. You have designed your flux. You believe that you did everything correctly. Now, how can you actually show that you have a fractional quantum Hall state? Now, of course, as a theorist, one would say, well, of course, there are lots of things one could do numerically, right? If you know what is the system that you have designed, maybe we could do some ED or some DMRG to characterize the state that we believe we have created. For example, we can calculate the many-body spectrum, we can calculate the entanglement spectrum, maybe the particle entanglement spectrum, which is what you get when you consider a bipartition in terms of particles and not in terms of geometry. And if you do so this is really a numerical experiment performed by Cécile Replin, you will see that, well, this is again the x-axis is the flux. You will see that there are gaps in the many-body spectrum in different regions. So these different regions are different candidates for fractional quantum Hall states. But now if you look at the particle entanglement spectrum, and if you now count how many blue states you have here below this gap, you will see that this counting is actually or exactly corresponds to the number of states that you would expect for a Laughlin state. So what is the number of state that you would expect in the particle entanglement spectrum? It actually corresponds to the number of quasi-holes that you can actually generate in the system. And this number of quasi-hole is a topological invariant and a topological fingerprint of your system. So this is like a very rigorous numerical way to say, yes, in this box, there is a Laughlin state. Now, something more practical, and this is the last thing that I will present now, something more practical is to look at the so-called strata response, which is really a static measurement, which is performed at the level of the local density. So you have particles in a box, right? Think about this little experiment here. You have a certain density profile. This is a typical density profile with some plateau in the bulk, right? We have an incompressible state, and we have some peaks on the edge. The edge, as we will see, will play the role of some reservoir. And what strata tells us is that the quantized hole conductivity, which is nothing else than the many-body Chern number in the system, is actually given by the variation of this density plateau in the bulk with respect to the flux alpha, right? So if you look at this little sketch here, this is a situation where we are actually in a Laughlin state. And what you can see is that by slightly changing the flux, so by looking at the variation d alpha, there will be a transfer of particles from the bulk to the edge, or vice versa, from the edge to the bulk, such that this raw bulk value will actually be increased or decreased according to the many-body Chern number. Okay, and so this thing can be verified numerically. This is, again, the numerical experiment that Cécile performed using 10 bosons in a box. And you see that when you plot d rho over d alpha, where d rho is, well, rho is this raw bulk quantity here in the shown here on this plot. If you plot d rho over d alpha as a function of alpha, you will see that all the points nicely align along a plateau at the value 1/2, which is indeed precisely the many-body Chern number of this Laughlin state. Now, beyond this blue region, there are other kinds of states which are not necessarily incompressible states. This is also what we see here. We might have compressible or incompressible states, but in those regions, we don't have any reasonable strata response. Okay, so I will just end with just a list of outlooks and things that we actually would like to do now with these fractional quantum Hall states. I will not have the time to go through all of them, but obviously there are many, many things to explore. I just partitioned these ideas into different sections. One would be to look at bulk responses. So for example, one could look at fractional charge pumping. We could look at quantized circular dichroism. We could look at quantized Hall drift. One could also explore the edge physics. So one could do edge spectroscopy to resolve, for example, the conformal field theory predictions on the edge of the system. One could do edge dichroism, something that we explored recently that can give information on the many-body Chern number, but also on the shape of the quantum Hall droplet. Recently, we also thought about injecting an impurity on the edge of a quantum Hall droplet. This creates a very exotic polaron, which we termed chiral polaron, which could exist on the edge of quantum Hall systems. Alberto Nardin and Jacopo Carusotto also investigated very beautiful nonlinear dynamics that take place on the edge of these quantum Hall droplets. And of course, there is a lot of interest, of course, in detecting and manipulating these anyons. There are several ideas, again, by Fabian Grust and collaborators on binding impurities to quasi-holes and then manipulating these quasi-holes by addressing these impurities. And I think I'm essentially done now with my part, and I think it's a good time to move to Julian's part. Thank you very much.
Thanks a lot, Nathan, for this very, very nice introduction. I would say we immediately go to Julian's part and then reserve all the time later for questions.
Let's do that.
Good. That works all with the sharing. Can you confirm that this is fine?
Yes, all good.
Excellent. Thank you very much. Yeah. So let's just go into the experiment. Nathan gave this very nice introduction about what can be done and what has been done and why we want to do all these things. Now, we asked ourselves, how can we use now these code atoms techniques in optical lattices and to go from the weakly interacting systems that Nathan mentioned into a system where we observe strongly correlated physics, and in particular, the ground state that corresponds to a fractional quantum Hall state. And the system that we are working with is an optical lattice in our case. It's an optical lattice which has a particularly amount of atoms. There are thousands of atoms here in an optical lattice. And the moment that I zoom in, you see that this actually is a lattice with individual lattice sites. And with a very high fidelity, we can detect whether on a given lattice site there is an atom or that there is no atom. So what we do is we perform a fluorescence image, and from that we can directly see if a lattice site was occupied or if it was not occupied. So the system that we're working with looks like so. It's a vacuum chamber here, which I depicted in this cartoon. And there's an optical imaging system, which consists of lenses both inside and outside of the vacuum chamber, which at its focal point has an optical lattice with the atoms, which is actually built by these green beams here. So we have an optical lattice, a two-dimensional optical lattice here in a single plane where we can now load our atoms. And we have this CCD camera outside of the vacuum, which can now perform through this high-resolution imaging system a single-side resolved image of the atoms. And here's again a picture of those atoms, and the zoom in, and then we binarize this picture and determine whether on a given lattice site we had fluorescence counts. That means there was an atom or none. When there was no atom on the lattice site present. And that's very beautiful because essentially it gives you noise-free data. Yeah? So it binarizes the fluorescence counts that you may have had in your original picture, and what you end up with is this kind of matrix, which is just tells you if you had an atom on a given lattice site or not. So a great tool that's been used over many different experiments nowadays. It happens actually that this was one of the very first experiments that was built and that had these capabilities. And what we added here to this experiment here is also the possibility to project local potential. So not only image through this objective, but also use it the other way around and send a light through this objective, through this imaging system, onto the atoms. So in this case, it's not resonant light, it's far off resonant light, just like the light that we also use for the optical lattice. And that means that it acts in our case as a repulsive potential. So the laser intensity is directly proportional to the repulsive potential for the atoms. By structuring this light, we can lift the potential on each lattice site individually. We can bring it up and down at will. So we have here some arbitrary shapes of potentials that we played around with, but you can also do more physically useful potentials. For example, we will later use a box potential that kind of builds a little wall around a certain area in this optical lattice. Or we can lift individual sites, for example, in future projects that would be very interesting to control the chemical potential locally in the system. Now, we've heard earlier that there is one challenge for us as a cold atoms experimentalist when we want to study magnetic phenomena, and that involves the magnetic fields. Atoms are neutral, and if we want to study any kind of effects, any phenomena that originate from magnetic fields, we need to do a little bit of work into this. And this is in our case implemented by these kind of additional beams that we project into this picture. So we have here the Fourier plane where we have two additional beams, these two orange beams here, and that's the Fourier plane and the imaging plane. So you can really see that compared to the lattice, they are a little bit off with respect to that. So when they then interfere at the place of the atoms, we get these diagonal intensity maxima and minima here. And again, they are far off resonance. So what they actually do is they lift the potentials on individual lattice sites. So the strength of the color here, so the more orange this is, the higher that we lift this individual lattice site. And you can see that this is not a static standing wave, but it's actually a running standing wave. So it's a moving one-dimensional lattice for the atoms. And the moving speed here is a so-called Floquet frequency. It's at a frequency that's ideally very, very far away from any of our intrinsic Hamiltonian parameters. And if then we add a horizontal gradient in our potential, which is depicted here by this black triangle, so we kind of create exactly this one-year Stark ladder that Nathan explained before. If we do that, we inhibit tunneling and we restore it then by the shaking frequency. The restored tunneling is then directly related to the relative phase at which these different lattice sites shake. And by the angle with which this standing wave would not then travel through the system, we can determine this relative phase, and by that we can determine the phase that is picked up on each little plaquette. And the phase that is picked up here is directly related to the flux of the system. And we can really tune this phase from 0 to 2 pi to any arbitrary value, which also means that we are working in essentially any range of magnetic fields that's physically possible, all the way down to a system where we would have a pi flux within in an individual plaquette side can be achieved here, which is completely unfeasible in solid state physics. And that's exactly why this question now of fractional quantum Hall systems in optical lattices or fractional Chern insulated that Nathan mentioned. Why that's such a relevant question also, because we can reach territory here that's just not feasible in solid state systems. So now we have all our ingredients at hand. Yeah, so we have our side resolved imaging. We can project and we can create magnetic fields for these atoms. And these atoms are, since they are in this optical lattice, they're tightly confined on the individual lattice sites, and that allows us to really also tune the interaction strength to very, very strong values, far beyond the tunneling energy. So we have all the ingredients here to go into strongly correlated topological matter. The observables that we can now access with the system are given by the side resolved images, and they are actually there's quite a variety of different observables that one can think of. So essentially what we do, but the moment that we take this fluorescence picture, is that we project it. So it may be in a big superposition of many different occupations on different lattice sets. And the moment we take this fluorescence picture, we project this state. So that means we would kind of sample in Fock state out of our many-body wave function. So these are the natural data that we get from the system. And of course, after we measure and we read out our atoms, we have to redo the whole work. We have to prepare the very same many-body state that may be in a big superposition of many, many different occupations. And then we will take another measurement, and this time we will pull at random another of those Fock state probabilities. So from that, we can really sample directly from the many-body state. So this is one of the observables that we can achieve here. From that, of course, directly we can measure local densities in the system. So on the side resolved level, we can measure the densities in the system, and also correlations between the sites and the particles. And not only correlations, say 2-point correlations, but actually of any order. We can also go to 3, 4, like any order as possible, because we have the full information on the density level. With a little bit of work, one can also go for off-diagonal observables here. So looking into local currents has been achieved, and also entanglement entropy or quantum state purity. There are protocols how one can also measure those. We're not going to use those observables in this particular experiments here that we were doing. I just wanted to highlight that we are not restricted to diagonal entries essentially of our state, but we can also go and measure any kind of off-diagonal elements. Now the Laughlin state, Nathan already mentioned it, but now the question is, of course, what does it mean for us when we look in the density sector, which kind of observables would be suitable for us? And if I look at the normal state and uncorrelated state, it looks like a fairly homogeneous density, so there's not much to see there. And if I would look at the Laughlin state in contrast to that, also not much of a difference here. But if I then zoom in and look exactly at the particles, I can see that on the left side, they look much more random than on the right side. So there's actually a correlation in that state, in that Laughlin state. And that correlation does not directly reveal the vortex nature of the wave function, but this picture of particles repelling each other and therefore optimizing their interaction energy, so shielding the interactions in this Laughlin state, is very much captured already with a single snapshot. Yeah, so we find here on the right side that particles tend to be away from each other, whereas on the left side they are indifferent to the distance to other neighbors. We can capture this on the two-body correlation function. So what we find here is that for small distances it's suppressed, and then for very long distances we reach the uncorrelated state again. That's really one of the hallmarks of a Laughlin state, that we find that on short distances, up to on the order of the magnetic length, we find a suppression of the 2-point correlation function simply because particles tend to be away from each other. And it's a direct consequence of this idea that these particles, they encircle each other with these cyclotron orbits. So it's depicted here in this cartoon, and also very reminiscent to the cartoon that Nathan showed earlier. Now we're dealing with a very special Laughlin state. It's a bosonic Laughlin state, so in contrast to the fermions that you may encounter in real solids. And therefore, it's a little bit different from what you would expect in terms of the filling factor. For fermions, you would expect it maybe at 1/3. For electrons would be the simplest Laughlin state. Here instead, we're working with a Laughlin state at a filling factor of 1/2. So we only require twice as many flux quanta in our system than particles to observe the state. And that will determine the magnetic flux at which we would expect to find this Laughlin state for a given atom number in the system. Now, again, we expect this to be gapped. So this is another maybe experimentally feasible signature. So the filling factor, we would expect it to be a gapped ground state. We also expect that the density correlations are suppressed up to the magnetic length, as we already saw. And then one can try to do some kind of measurements of the fractional Hall conductivity. For instance, through the Streda formula that Nathan mentioned earlier, or through Hall drifts or other kind of measurements. So these are maybe the experimentally more accessible quantities. Looking at the particle entanglement spectrum is a very nice hallmark signature, but experimentally a bit very challenging to measure something like that. So the protocol to engineer now such a Laughlin state that we used in our system looks as follows. So we start with a Mott insulator where we have exactly one particle per lattice site. So we have we have fluorescence counts on each side here. And we build a little box around this to really make sure that this is exactly our system. And the first thing we do is we want to look at the simplest possible Laughlin state here. And in our case, this is a 2-particle Laughlin state in this box. And so we get rid of all the particles on all the other sides. So we start really with a pure quantum state with exactly one particle on these 2 lower left sides. So 1 particle per side. So we have 2 particles in the system. So our initial state. And then we apply offsets to these individual lattice sites in such a way that this is actually the ground state of our initial Hamiltonian. Yeah? So we have a Bose-Hubbard-Harper-Hofstadter model in our system, and we now tune all the Hamiltonian parameters in such a way that this is exactly the ground state. And from there now we move in an adiabatic fashion all the Hamiltonian parameters until in the end we reach a system that has Hamiltonian parameters that correspond to what we expect for the Laughlin state. So a strong interaction strength, much stronger than the kinetic energy, in order to have a kind of fairly flat band and dominant interaction energy, and the filling factor that we expect of 1/2. So just the magnetic field, the artificial flux here should be on the order to have 1/2. So these are the kind of parameters that we target as our final state. And once we reach this final state in this adiabatic ramp, we take snapshots, and so we sample in Fox space from our state, and from that now we can characterize our system. Now I told you that we do this adiabatic ramp, but Nathan told you it's a subtle thing, and it's not obvious that we are actually able to do this adiabatic ramp. So in order to convince ourselves to make sure that we really have an adiabaticity going on here and not maybe end up somewhere in the middle of the spectrum or in the big superposition of many different states, what we did also was to invert this ramp once we achieved our final state, to invert it and bring it all the way back to the initial state. And if we still find, after all of this, these adiabatic ramps, if we still find that at the end our state is predominantly in the ground state, our system is predominantly in the ground state, which now is again the initial state. If that's still the case, then we can really make sure that the ramp was an adiabatic ramp. So for us, it's more like a test to make sure we are really in the ground state. And it's a test also that our ramp was an adiabatic ramp, because if it's not an adiabatic ramp, we would expect excitations in the system that would show up in a different way than seeing the particles on the 2 lower left sides. Yeah, they would be on other sides then. So this was the first thing we did. So we did this adiabatic ramp, and we did it for different final flux values. And what we find is that indeed for a flux here at around 0.25 to 0.3, we find a gapped system, and gapped in the sense that we find a good fidelity to come back to our initial state. So we find good adiabaticity. We also find good adiabaticity if we are in a very weak weakly magnetic field, so very weak magnetic field. We also find that we are well gapped, and then at the intermediate level here, we find that our adiabaticity breaks down a little bit. So these dark blue dots here that show us the very final state. The light blue ones, they're just a reference to an earlier point during this ramp. So that means that we confirm here that for strong magnetic fields, we have an adiabaticity that is working. For a weak magnetic field, we also do have that, but in the middle it breaks down. So that's it's a strong signature that there's a point where we have a gap closing in the middle. So it's a kind of a spectroscopy that we're performing here of this many-body gap. And the signature, of course, for us indicates that there's a transition from a normal to a different phase. In our case, a topological phase transition from a normal to a fractional quantum Hall state. Now, of course, at this point, we're not really 100% sure. Is it really a Laughlin state? Is it really a Laughlin-type fractional quantum Hall state? And so what we want to do then first is to look at this seminal signature of the two-point correlations that would show us indeed what we find here is a state that is a fractional quantum Hall state that has this signature that I mentioned earlier of suppressed correlations on the short range. And what you find here is exactly those two-point correlations. So in the top row here, these are our experimental data, and the lower row here is the comparison with exact numerics of the ground state. And we indeed find here that if we go in the normal range, so in the low magnetic field area, we don't really find any strong correlations, whereas in the stronger magnetic field area, we did find that on the nearby lattice sites, so this would be our one lattice site and the second lattice site that we now correlate with, there we find a suppression of the two-point correlations. Yeah, and then if we increase the distance, eventually, actually, the suppression vanishes, and that's what you can find here with this red ring here. Really shows you that eventually the suppression is not there anymore. We can also perform a radial average that's maybe a bit closer to what I've shown, the way I've depicted it earlier, where here we find this very, very nice suppression here on the order of the magnetic length, which is for us about our lattice site. And then afterwards it increases, whereas in the normal range, so at weaker magnetic field, we don't find a suppression. There's a little bit of a suppression still going on because we have also still repulsive interactions. So particles tend to not be on the same lattice site, but that is much weaker and doesn't show us this nice vortex kind of correlations that we find in the fractional quantum Hall regime. So this was for us a very important moment when we realized, okay, this is actually a fractional quantum Hall state that we find here. Can we go beyond and show that indeed it is one that corresponds to this 1/2 state? And that's where the Strata formula came in that Nathan mentioned earlier. So we can measure the density on an individual lattice site level, and that also gives us access to exactly this charge redistribution when we change the magnetic field. So here you find two density distributions, once for a weaker magnetic field right at the beginning, right behind this topological phase transition. And then as you increase the magnetic field, you can see that the center sites here, the four center sites, their density increases at the cost of the edge. So the edge, there's density from the edge that is moved into the center. And now we can show this now. We can measure now the density on these central four sides as a function of the flux, and it should increase, and indeed it does increase, and it increases with a slope that is comparable to 1/2. So indeed here we find already that our state is definitely incompatible with an integer quantum Hall, and compatible, the conductivity is compatible with a fractional quantum Hall conductivity of 1/2. It's not this precision that you maybe are used from sort of state physics, but for us, it really showed us that we are on the right track here, and we're looking at a Laughlin state with a fractional quantum Hall conductivity of 1/2. Now, of course, for us, this is just the beginning of a very new chapter. It's really, we are entering a very exciting new era where we can look at cold atoms in optical lattices and study their topological matter. The first big step for us now will be to increase the system size, and we did some numerics to that actually should be achievable also for larger systems. There are several publications, several work here, for example, involving Butao, Wang, Felix Palm, together with Nathan and other collaborators, how one can now start looking at these small plaquettes, these small systems of 4x4, and increasing the system size by attaching one after the other. The elevator was already mentioned. That's definitely one of the first big steps that we want to achieve. And then we can look at the exciting new observables that go beyond of what we've observed so far. We can, for example, look at quasi-holes. So by adjusting the chemical potential locally, we can maybe trap a quasi-hole. That would be a very exciting thing to do. There are proposals how to braid them, how to move them around each other, and extract their phase and their anyonic nature. And then ultimately, we also want to move away from Laughlin states and go to more exciting states. The Pfaffian states, for example, are predicted as at a filling for bosons at 1 instead of 1/2. And these host now non-abelian anyons with even more intricate signatures in their braiding behavior. So these are all on the agenda for exciting new physics of the next couple of years. We now in Vienna we also want to contribute to this. So the experiments here all done in Boston. In Vienna we are building our new experiment, which is built to now also look into exactly those kind of physics, into topological matter. And ideally also for larger system size. So we are optimizing everything to get these systems larger in our system and to have sufficient control to also reach these more exotic Pfaffian states in that system. I want to highlight that we are just one of those different platforms that do these. Here, Nathan mentioned earlier other people that work with optical lattices and topological systems. So Monika Eidelsberger in Munich, Wolfgang Kettel at MIT are some of those people. But other platforms that also look at topology with cold atoms are rotating traps. So you can do very similar physics by rotating, for example, microtraps. This has been achieved recently in Selim Johannes' group, where they were able to create a Laughlin state of two fermions. And another big branch are also photonic systems that actually already a couple of years ago were able to look at Laughlin states of light, where you had photons that entered the Laughlin state. In John Simon's group in Stanford, and also recently on photonic platforms, realizations of Laughlin states or fractional quantum Hall states in photonic systems in John Ray Pan's group. I want to highlight the team that has been doing this. So the boson quantum gas microscope group in Marcus Greiner's group in Boston at Harvard, together with really nice collaboration with Fabian Grust and Cécile Repellin, who on top of Nathan were helping us with a lot of the theoretical concepts and were really crucial in all the experiments that we did here. So it was a very nice joint theoretical and experimental effort that was done here with this experiment. So with that, I want to thank all of you for your attention, and I would be at the end here.
Thanks a lot, Julian. Wow. I think I understood now way more things than before. Thanks a lot for describing all of this.
You're welcome. Thank you.
So I think we should now open the room for questions. Please just raise your hand or unmute yourself and simply ask whatever you like. If you don't mind, I would actually start because you have now done this for a lattice which has 4x4. It's 4x4, and you have also already said in your summary outlook slides that you would like to make the lattices bigger. May I ask, what is actually the problem of making it bigger?
The major so there's actually, like, technically we have a lot of lattice sites. I showed you it's a big system, so that's not necessarily a problem. The only challenge is that we are still adiabatic. So we have we want to be, so the bigger we are, the smaller will be the many-body gap. So that means the adiabaticity will become a bigger challenge. And to really stay in exactly the ground state, the biggest challenge is simply to make sure that we have a sufficiently long coherence time to do our ramp still adiabatically. I think this is, from my side, I think the main challenge. So what we need to be able to do is have a longer coherence time. And we're already pushing it with these experiments here. So these Floquet systems, they're prone to noise. There are a lot of channels in which now particles can be heated and then you're going out of your actual Hilbert space simply because you have another energy scale with this Floquet drive. So what we need to be able to do is to have systems where we have a better energy separation between the drive and our Hamiltonian parameters. And that's one of the goals that we want to achieve with this new setup now in Vienna. But I think these are the challenges. There's nothing fundamental that prevents us from doing so. And in fact, also there have been now already some publications have proposed better paths than the one we've used, so more efficient paths, which indicate that we could actually, with the coherence times that we already achieved in this experiment, we could already generate Laughlin states of larger system size. So I think we are on a good track here, but it's just some work to do.
Yeah, thanks a lot. Okay. If you don't mind, I would actually keep asking, but this time to Nator. There was a slide where you were talking about what are conditions when a Laughlin state will typically emerge. And you had there something like quantum geometry, a flat quantum geometry. Could you maybe just explain a bit more in which sense this is related to geometry? So which type of metric are you looking at, and so on?
It's a very delicate subject because some people would argue that you can even generate fractional quantum Hall states without any Berry curvature. I mean, there's even a provocative paper by Steve Simon showing this explicitly. So it's a very delicate subject, but indeed based on theoretical input, but also mathematical intuition and numerical analysis. Indeed, it seems that fractional quantum Hall states like to be stabilized in situation where the quantum metric and the Berry curvature are relatively flat. And this also comes with now mathematical structures. I will not go into the details because it can be very, very technical, but there are some relations between Berry curvature and and quantum metric. There are some bounds that one can derive, and one can show that bands which are similar to Landau levels typically saturate these bounds. So people propose these kind of criteria. So if the Berry curvature and quantum metric satisfy these or these conditions, then it seems that the bands mathematically or at the quantum geometric level are similar to Landau levels. So there are mathematical structures which are scalar structures, which are known in mathematics and also in quantum field theory. So these scalar structures which are present in the Landau levels, so they're kind of hidden in the Landau levels, they seem to be the right mathematical structures that one should generate at the level of the Bloch bands. This also comes with this vortexability condition. If you ask someone like Duncan Haldane, he will rather look at things from a real space point of view, because when one thinks about quantum geometry, one typically thinks about quantum metrics and Berry curvature associated with Bloch states. But people like also to think in terms of Wannier functions, things which are localized or almost localized in real space. And people like Haldane would argue that these are actually the fundamental things that one should look at, which are really the structures of Wannier states in real space. But as I said, this is ongoing research. There are lots of ideas which are not yet published and discussed. I mean, this is still openly discussed in workshops which are taking place today.
Okay. Thanks a lot for explaining this.
Okay, you're welcome.
There is now a question from the Gärtner group. Please.
Hi. Thanks, everyone, for the nice talks. I have a technical question to Nathan. So, Nathan, you were talking about particle entanglement entropy, entanglement spectrum. And I was just wondering how this is, because you have identical bosons, right? And so, yeah, what is this? I thought if you have identical particles, it only makes sense to talk about mode entanglement, or so. Can you explain?
Indeed, I think I missed a part of the question, but I think I understood. So you're basically asking if it makes sense to introduce this particle entanglement spectrum for identical particles, and
Yes.
maybe how it is done. So this is well, first of all, this is done numerically, right? As Julian nicely said, this is not something that one would measure, because you basically have to take your density matrix. So in this case, we're thinking about having a pure state, which is this Laughlin state. And then the idea is indeed to trace out some particles in your system. And now this is the step that I think you're asking about, which is how you do that. And the idea is that at the level of your ED calculation, you can actually really split your system into two and say, let's say I have 5 particles, right? And I can really split my space or my states in terms of these 3 particles on one side, 2 particles on the other, and I can basically look at the reduced density matrix, which happens when I integrate out well, the degrees of freedom associated with these 2 particles. And this is something you can do at the level of ED, essentially. So you numerically construct this reduced density matrix, and then you look at the spectrum of this reduced density matrix. But it's really a numerical trick. I wouldn't know how to do this in real life.
Yeah. Okay. Thanks. That clarifies it. Yeah.
You're welcome.
Okay, so Botao Wang, please.
Yeah. Hey. Hey, Julia, thanks a lot.
Hey.
Thanks a lot for the very nice talk. So I have a question regarding the slide of next steps. I guess you mentioned the fermionic system. So I would be curious why fermions. Wouldn't bosonic system be more easier? Or so can you comment why using fermions, let's say?
So the system is actually built for both bosons and fermions. So it's lithium-6 and lithium-7. It can do both in the future. One thing we would like to do is to extend also the notion of like of Laughlin states to fermionic realizations, because that's something we haven't looked into yet, and it would be a closer realization also to solid state systems. But it's true, we think we want to do both. Yeah, we want to do both. We want to do bosons and fermions.
Okay, thank you.
Yeah.
More questions? Question mark. Okay, seems that everyone is satisfied. Let's take this as a good sign and thank the speakers electronically again. Right. Okay.
Very much, but thank you for inviting us. That was really pleasant. Thank you.
Yeah, thank you. It's a very, very exciting format. I'd love to be part of it.
So maybe a short announcement. This talk will of course be uploaded to our YouTube channel, and we will have the new qmeets in roughly 1 month. Switching topics, our speakers will be Martin Plenio and one of his postdocs, who will now become a professor in China soon, Dayu Yang. And they will talk about quantum sensing and how to get the best precision in many body systems. So I hope to see many of you there. I thank again all the speakers and all people who came here today. And yeah, just have a great day, everybody. See you next time.
Have a great day. Bye-bye.
Yeah, bye. Thank you.
Bye.